Hello, and welcome to another one of my supplemental lectures for my PSYC 440-640 class. This is called Experimental Methods. I'm teaching it as I do every spring semester. This is spring 2016, and here at NDSU. This little supplemental lecture is called Dealing with Problem Data. And really what I'm going to focus on are some strategies, or at least just outline some strategies that you can use when you have a data set that includes outlying values, or where you have concerns about violations of various assumptions that you're making for different parametric tests that you're doing. In a previous lecture that I gave in class, I talked about what I think of as kind of my basic approach to inspecting a data set, the data that I've gathered or that someone who I've worked with has gathered from a study that they've done. And one of the first things is to look for outliers. I like to look for outliers first because finding and inspecting, kind of interrogating outliers can helpfully stop a lot of problems which down the road and further on in data analysis are very difficult to fix. So for instance, you could find values in your data set, and depending on the quality of your notes from your laboratory work, you might be able to realize that a certain person has this unusual value because your computer wasn't working that day, or because he or she filled out a particular questionnaire incorrectly. And finding and hopefully fixing those problems first means that other problems like weird looking distributions or parameter estimates that are biased are less likely to occur. So it's often a good first step to look for outliers, and if you can, do something about them. And I'll talk a little bit about what you can do about them later in this mini supplemental lecture. Another thing that I like to do is consider some of the assumptions that go along with many of the statistical tests that we do, things like regression, ANOVA, which is of course just a special case of regression, and so on. But think about the context in which we're making these assumptions. For instance, the assumption of normality can mean different things depending on what we're talking about. Are we talking about the shape of a sample distribution? Are we talking about a distribution of errors associated with a model, or so on? It's important just to think about what is really concerning us, rather than say, oh, we must assume normality, therefore all our data must be normal. And I've talked about this a little bit in a previous supplemental lecture on distributions of data, and I've also talked about this a little bit in class. Finally, the third step, or the third and fourth, depending on how you count these things, is to evaluate some of these assumptions like homogeneity, variance, normality, etc. And I encourage people to first take a graphing approach, try and make some box plots or histograms, probability plots, etc., to visually inspect data to look for violations of assumptions. There are also, of course, various statistical tests which test for violations of assumptions, like the Levine's test that looks at homogeneity of variance, or the Kolmogorov-Smirnov test that looks at normality. These can be really useful, but they suffer from a problem where they tend to be underpowered in many of the situations where we care about violations the most, particularly situations where we have small-ish sample sizes. In those cases, our tests of our assumptions don't have a lot of power to detect effects, and those are the very cases where we worry the most about violations of assumptions. So anyway, taking this basic approach, what happens if you have concerns about your data? Like, for instance, you find outliers, what should you do about that? Or your sample has an odd-looking distribution, and for reasons, after careful reflection, you decide that that's a problem. What do you do about a situation where you think you might have violated an important assumption? And I put a little bar down here at the bottom of the screen just to remind myself really, that all of these issues, outliers, oddly shaped distributions that may involve or may lead to violations of assumptions, all get a lot worse when we have small samples of data. With large samples of data, these things are typically not that big a deal. So having a single outlier in a sample that has only 10 cases is not good. Having a single outlier in a sample that has 50 cases, not that big a deal. One of many, and there are so many reasons to have large samples of data when doing research. Okay, so what do we do about these? What are some strategies? Here's a few thoughts I have about strategies for solving problems with data. Let's focus on outliers first. Recall that a lot of the time that we're making models of data or comparing models of data, we're using means, sample means to estimate population means. This is one way that we aggregate data. We make models often by trying to minimize the sums of squared errors around these means. And as I've discussed in a previous supplemental lecture, means are very sensitive to outliers. So if we have a data set where we have outlying values, we might be concerned that those outlying values are among the other problems they might be indicative of, they're at the very least pulling our mean away from where it probably should be. So there are two strategies that go along with outliers, or two strategies that can be used to address them. And simply put, one is just to remove outlying cases, and the other is to change the values of outlying cases. So focusing on that first one, removing outlying cases. There are two options that we typically have. One is listwise, or what's sometimes called variable deletion, where we remove just the missing variable for a given case. So if we have 10 people in our data set, which is a small sample size, which already is a problem, but let's say person number 9 is missing a variable or value for one of the variables that we measure. Listwise deletion would be just to get rid of that variable for that person, or delete that variable when we analyze, or delete that person when we analyze that variable. Another option is case-wise deletion, where we remove that value and all other values for that case. Essentially, we delete the whole case. Person number 9, I think I said, is missing one value for one of the variables that we measure, but we get rid of him or her entirely. Doing so is pretty extreme. It's sort of a Procrustean maneuver, but it ensures us that we end up with a complete data set where every case, every participant in our data set has complete data for all the variables we measure. So listwise deletion and case-wise deletion. There are pros and cons of each approach. Obviously, listwise deletion is more forgiving. We're not so quick to get rid of data. Case-wise deletion is a more severe approach, which gets rid of data that can obviously can cost us some power in our analyses, but it also helps us keep our groups, if we have a groups comparison type analysis, balanced, which is desirable for all sorts of reasons that I'll get to in future lectures. You have two options that the researcher should carefully think about. Researcher should also carefully think about his reason or her reasons for either removing a particular variable for a case where there's a missing value, or removing that case entirely. Ideally, again, you should have a good reason for doing this. Maybe the reason is that the case comes from a different population other than the one that you're studying. After looking at the data and after perhaps reviewing your laboratory notes, you think, oh, we were studying this one population, and perhaps person number 9 really is from a different population that ought not to have been included in our sample in the first place. Maybe deleting that case makes sense because there's some sort of a measurement malfunction. The computer tried to update Adobe Acrobat that very day that you were running the subject, or the photocopies of your questionnaire data were only photocopied on the front side, so the back sides of all the questionnaires are missing. That stuff happens, and if there are good reasons why a particular variable for a particular case, or a particular case entirely, should be removed, then by all means do so. Having bad data in your data set isn't helpful to anyone, least of all yourself, of course. The temptation, though, is to kind of prune or to cherry pick your data, only including cases that really seem to fit with your hypotheses, or removing cases that seem to be incongruent with your hypotheses or your predictions. This is a bad idea for all sorts of reasons. Years ago, I remember talking to a graduate student who was describing rather proudly one of the projects that he'd done in his laboratory at the time, and he was saying that he'd observed this particular effect in a manipulation that he'd done, and he said quite casually, I had to remove 40% of the cases in my data set. And I did probably some sort of a double take, because I thought that was a very large amount of data to remove. It seems likely to me that he'd sort of deliberately or unwittingly had cherry-picked the data, finding only the small and rather biased subsample of his participants for whom this particular effect held, and ignoring or removing literally all the others. People who do statistical data analysis often say we should fit the model to the data. We shouldn't fit the data to the model, and what they mean is, or what they're referring to, is this kind of conceptual equation of data equals model plus error. We should take the data we have, that is all the participants, all the cases in our data set, and we should try to fit or build our model, our set of predictor variables, in such a way, or set of parameter estimates for predictor variables, in such a way as to fit that data, rather than having a model in mind and then cutting out or trimming out all the values that don't quite fit in with our model. So, a related issue or a related idea that comes up with removing cases is, in some areas of some statistical programs, for instance SPSS, you can find the trimmed mean. The trimmed mean is just a calculation of the mean after extreme values are removed, and you can trim means in different ways. Sometimes it's a percentage, so there are ways to sort of fiddle with this in SPSS. You can have a mean calculated after the top and bottom 5% of cases are removed, or you could trim the mean by removing the top and bottom values that exceed 2 standard deviations from the mean. Both approaches are sort of are possible. An issue that's worth acknowledging, especially with the latter of these two, is that estimates like the mean and the standard deviation are influenced by the presence of outliers. So just simply trimming off people who fall a certain number of standard deviations above the mean can be problematic if the mean and the standard deviation that you've calculated have been influenced, of course, by those outlying cases in the first place. The other thing to acknowledge here is that this, like any other approach of removing data, is somewhat problematic because we're kind of arbitrarily getting rid of people. We should, at least in my judgment, ideally have good reasons to remove outlying cases, reasons that we can track back to our laboratory notes or to our records of what was really going on that day when we were gathering data for that particular case, that particular person or animal or whatever. So one broad approach for dealing with outlying data is to get rid of the data in some way or another. Another approach is to change the values of the data. So to take a given outlying value and give it a different value that's less outlying. This approach is called Windsorizing, and there are actually a lot of different methods that you could use for Windsorizing. So you could take the most extreme value, your worst outlier, and instead of having that person retain his or her score on a particular variable, you could give him or her the score of the next most outlying person, so kind of pulling them in a little bit. Or you could take all the outlying values that have extreme outlying values, and you could give them new scores that are equal to the mean plus 2 standard deviations on the variable that you're measuring, or the mean plus 3 standard deviations. Although, as I noted on the previous slide, you have to remember that the mean and the standard deviation have already been kind of influenced by the presence of outliers, so that's maybe not exactly the best approach. Bottom line is there are different ways to Windsorize data, and people who think a lot about how to deal with outliers have come up with lots of clever ways of doing this. In general, these approaches are called they're called Windsorizing, but you also hear people say that we're bringing outliers to the fence. What they mean is they've established some sort of maximum value that can occur within the distribution of a particular variable, and they're bringing all values that exceed that maximum down to the maximum. They're bringing them into a fence. And again, there are probably some good ways to do this. I would argue, as I have kind of across this little mini lecture, that we should always have good reasons for this. We should have kind of a rationale that backs up our choice of Windsorizing. So for instance, it may be the case that within our area of study, people typically windsorize their data in a particular way, or even better, methodologists in our area have compared different windsorizing strategies and have found that one produces the least amount of bias in estimating parameters, or retains the most amount of power in terms of subsequent analyses you can do, and so on and so on. That's probably preferable than the individual researcher just fiddling around with different strategies until he or she finds a set of data that give him or her a significant effect, p less than 0.05. That's probably more questionable. So there are different ways of dealing with outliers. I mean, I guess I've kind of sketched out the two broad approaches here. I'll move on now and talk about different ways of dealing with violations of assumptions. And here, the basic idea is that the statistical tests, many of the statistical tests, I guess really all the statistical tests that we do, make various assumptions about the data that are being submitted to them, or various assumptions about sampling distributions for their test statistics, or various assumptions about the populations that the data was drawn from. It's important to think a little bit about the context that these assumptions apply to, and as I've done in a previous supplemental lecture, I've talked a little bit about the assumption of normality and the assumption of homogeneity of variance. Are we talking about the sample distribution? Are we talking about the error distribution? Are we talking about the sampling distribution? It's worth thinking about. To just summarize, there are assumptions like assumption of normality, assumption of homogeneity of variance, and as a very general point, violations of these assumptions can be problematic. Oftentimes when there are violations of assumptions, for instance, for homogeneity of variance in a groups comparison type analysis like in ANOVA, a result is a loss of power for that test to detect effects which are really there. Worse, there can be situations in which their odd or spurious effects are more likely under violations of assumptions. So there are good reasons why we might want to address violations of assumptions in our data. So focusing here on the two assumptions that have most to do with your data analysis, that is non-normality and heterogeneity of variance, non-homogeneity of variance, it's worth quickly acknowledging that it isn't always a problem if your sample data is not normally distributed, for instance. And it's not necessarily, although it can be a problem, if in your sample data different groups have unequal variance. All of this is much worse, as I've said before, when we have small samples than when we have large samples. It's not inevitably a problem if you look at your data and it isn't perfectly normally distributed in your sample. I've talked about that a little bit in previous lectures. Nevertheless, if you think you might have a problem with your data, there are three broad strategies that you can apply. One is you can transform your data set. Two is you could approach your data set using so-called non-parametric tests. And the third is that you could use robust tests. And I'll just sketch out a little bit for each of these. But as I've kind of noted here, it's worth acknowledging once again that these strategies can actually help with outliers if you have outliers in your data set. But in my judgment, at least, you probably should have thought about outliers first, because if you can fix problems with them, that tends to mitigate some of these problems that you can run into with violations of assumptions. So let's look at the first of these three strategies. Transforming the data set. There are actually a large number of different transformations we could do to our data, and they have different types of effects. Often the ones that we are interested in are transformations which reduce extreme values or change the overall shape of a distribution. Once again, and I know I'm being kind of repetitious here, I think it's important to have good reasons for doing these types of operations, reasons that can be backed up by established practices within your field, or which have been explored by methodologists who've looked at the data in your field, rather than just fiddling around with different transformations. I should also say a transformation is an approach or an operation which changes not just one, but all the values in the data set. So if you were back up for a second, if we're thinking about windsorizing the data set, that's a process of taking specific values, outliers, and changing them but not changing other values in the data set. Transformations, the ones I'm going to talk about in the next few slides, change all the values in the data set in ways that hopefully are useful. So here's an example of log transformation. We have some data here from an example that comes from our textbook and that we've talked about briefly in class of a rather skewed data set. It's a positively skewed data set where there's this kind of lumping of values mostly on the left-hand side of the distribution, and then kind of a long tail extending out on the right. If you apply, or if you take the logarithm of all of these values and then plots those resulting log values, you get a distribution that looks a little bit like this. And people like log transformations in some contexts because it tends to reduce positive skew. You can kind of see that here. It sort of gives us a distribution which is not as skewed, it's more symmetrical, and it does begin to resemble a little bit more of a normal distribution, which for different reasons we might like to see in our analyses, even though we don't always have to have a normally distributed sample of data for much of the testing that we want to do, as I've talked about before. Here's another example. We could take that same data set and we could square root transform it. So you just take every single value in the data set, compute the square root of it, and then plot all those values, and you see something that looks a little bit different. It's different than the raw data, but similar actually to our previous example of log transform data. Once again, we've reduced positive skew. We have a distribution that looks much more normal. We've also, this procedure is often also used to stabilize variance. What that means there is it tends to reduce the variance of the data, and if you square root transform two different groups that maybe have rather different variances, after square root transforming each of them separately, the variances of those groups will be a little bit closer together. So it's a way of dealing with heterogeneity of variance if that's a problem, which it sometimes can be. Here's another example. We could take our raw data and we could do a reciprocal transform on it. Again, taking each value in the data set, and in this case, putting 1 over it. And if we did that, we would again reduce skew. We kind of take the impact of large values and make it make that impact much smaller. Interestingly though, reciprocal transformations reverse the scores of values. So for instance, if someone had a very large value on some variable you're measuring, once you compute the reciprocal of that person's score, he or she now has a very small value of it. And sometimes people will try and avoid this by reversing scores before the transformation. So they'll take the highest score and subtract every individual score from it, and then compute the reciprocal of that as a way of kind of reversing or canceling out that reversing effect, I suppose. This raises actually a kind of an interesting issue. And that interesting issue is when we have untransformed data, and then transformed data, we're talking essentially about values that are on very different metrics. So if you think about a variable that has a kind of a naturally understandable metric, like the number of alcoholic drinks people consume during a day, what someone's reaction time is in seconds to a particular task on a computer, it's fairly easy to understand what large or small values of that mean. Once we transform that data, and we're now talking about the log transformed number of alcoholic drinks people consume per day, or the log transformed reaction time in seconds that someone needs to complete a task, it becomes a little bit more difficult to think, at least for most people, I suppose, unless you're a rather clever mathematician, to think about what it exactly is we're measuring or what exactly is we're talking about. At its worst, I think this creates kind of an apples and oranges problem where it becomes sort of difficult conceptually to map on our results that we see in transformed data onto what they kind of mean in terms of untransformed data. So to transform or not to transform, well, clearly there are all sorts of different examples that we could come up with, or that some of you probably have experienced, where transforming data is useful, and probably many, many more where it isn't. as a very general point, transforming data can correct some problems. Problems like non-normality and heterogeneity of variance can be helped sometimes by transforming data. But transforming data can also create problems. It can be somewhat more difficult to interpret results because the data are now in a new metric. And depending on what that metric is, it can be sometimes hard to sort of think about what the values really mean now that they've been log transformed or put in inverse or etc. etc. I've read different stats textbooks over the years, and it's just interesting for me to note that some authors are very keen on transforming data. They think it's a very sensible thing to do, and they like this sort of improved, improved approach that you get vis-a-vis assumptions that your tests are making. Other authors just seem to really dislike this and say, like, well, you can transform your data, but really you shouldn't, because you'll just end up confusing yourself. I suppose to some extent it's a matter of personal taste, but as I've said before in this supplemental lecture, I think it's really worth considering what are the standard practices in your field, what are the practices that have been best kind of developed and explored by other researchers, other methodologists, before just kind of fiddling and finding your own way that sort of seems to make sense to you. Anyway, another broad approach for dealing with violations of assumptions is to choose a different kind of statistical approach entirely. I'm talking here about non-parametric tests, and non-parametric tests in a way are just a whole hodgepodge of different procedures that involve fewer assumptions than do many of the tests that we're more familiar with, like t-tests or ANOVAs or the like. These tests, non-parametric tests, used to be called assumption-free tests, which is a bit of a misnomer because it's not the case that they make no assumptions about data. They just make different assumptions. And what's also interesting to note is that most of them are a lot like our more familiar so-called parametric tests, except they work by first rank ordering data. So instead of having values that have vary continuously and might include outliers or an oddly shaped distribution, all the data is rank transformed. So we talk about people in terms of whether they're first, second, third, and so on place within the data set, and then we apply to them various procedures that look a lot like our familiar parametric tests. One of the knocks against non-parametric tests is that there are a lot of them, or there are a fair number of them, but they're fairly limited in the types of applications that they can be put to, and that in terms of complex analyses, like for instance where you have a situation, a test that involves multiple predictor variables, they can be difficult or maybe even impossible to do. So I know there are people out there who work a lot on non-parametric tests. There are people in the stats department here at NDSU who specialize in them, so I don't mean to impugn this area or certainly not my colleagues' work, but my sense and the sense from some of the authors I've read is that non-parametric tests are great when you can use them, or they can be great when you can use them, but there are just a lot of situations where you can't easily use them. You sometimes hear it argued that non-parametric tests have lower power to detect effects, but that's a little bit of a misstatement, I think. It's a vague statement because it doesn't make clear what the comparison is. Non-parametric tests have less power to detect effect than parametric tests where assumptions are not violated. That's usually the case, but if you were to compare a non-parametric test to a parametric test that was analogous to it, but in a situation where the assumptions necessary for that parametric test have been violated, you might very well find that the power was greater for the non-parametric test. So again, a criticism or a knock you sometimes hear. I don't think it's entirely fair. Maybe the more important point, at least as far as I'm concerned, is that non-parametric tests are somewhat more limited in the applications that you can put them to. So I didn't say a lot about non-parametric tests. Unfortunately, I'm going to say even less, I'm afraid, about robust tests. Robust tests are this third option, and they are a collection of different procedures that are designed to be more tolerant of violations of assumptions. Hence, they are more, or that's where we get the term robust. They don't lose as much power. They don't produce as many problems with bias in situations where there are violations of assumptions. To understand what robust methods are, it's worth reflecting on the fact that our kind of classic statistical tests or analyses that we are familiar with, involve finding probability values that are based on distributions of test statistics for the null hypothesis. These are sampling distributions, and back in the day you would have to look up in the textbook the particular probability value of a test statistic for a given number of degrees of freedom under the null hypothesis. Nowadays, of course, your computer program almost certainly does this for you. This approach of finding a test statistic and then looking up its probability in an assumed sampling distribution really dates back to the early days of statistical test development. Back before modern computing methods, when people like our man R.A. Fisher here, or Carl Pearson, or their other colleagues had to work with simple adding machines or by human calculation. And it was very difficult to compute sampling distributions. So instead, assumed distributions were substituted in that had known mathematical probabilities, which could be computed easily in tables. These classic statistical tests make assumptions about data because these assumptions are necessary to talk about the probability or improbability of a particular test statistic. So we might assume that the sampling distribution for the t-statistic under a certain number of degrees of freedom is going to have a certain shape. And if we can make these types of assumptions, we can know, or we can talk about the probability of our particular observed test statistic value in that null distribution. Nowadays, there are all sorts of relatively modern statistical techniques where we actually compute a sampling distribution, or we simulate it by successively resampling our sample of data to create many thousands or tens of thousands or hundreds of thousands of simulated studies, each of which will yield a value for the particular test statistic that we are interested in. So back in the day they couldn't, of course, run a particular study a very large or of course infinite number of times and create a sampling distribution. So instead they had to make assumptions about what that sampling distribution would look like. Nowadays we can simulate what it would look like if we'd run our study 100,000 times or 1,000,000 times or so on. These approaches have different sorts of names. A general name that's sometimes applied to them is bootstrapping, because the idea is you're using your sample data to kind of pull a sampling distribution up by its own bootstraps. These approaches offer kind of a flexible way of approaching data analysis that makes somewhat less assumptions about the type of data, about what's going on in the data, and they're useful in situations where the classic assumptions associated with statistical testing are untenable. Unfortunately, robust methods are difficult to implement in a lot of statistical packages, especially SPSS, the one that I'm the most familiar with. There is a module for bootstrapping, but it costs extra money, so I haven't yet purchased it or had NDSU purchase it for my students. Maybe one day I will and get more comfortable with it. There are options for doing bootstrapping in R, which is, as you know, a free statistical programming language. R is a little bit tricky to learn, but one of my major motivations for learning how to use R is to be able to use it for simulation analyses and for bootstrapping. A lot of people have written about robust data analysis. Probably the most famous name, at least the one I'm the most familiar with, is Rand Wilcox, who literally wrote the book, or wrote a book, about robust estimation and hypothesis testing. I can't say that I've read it yet. I do really want to, because it is supposed to be the real definitive treatment of the topic. And it's interesting, I'm told, and very readable, I'm told. Apparently Wilcox is a good writer. Anyway, that's not a lot of information about robust testing beyond just sort of generally what it is. It is one of these three approaches that we might take in situations where we think we've grievously violated some of the assumptions that go along with our familiar statistical tests. The other options being transforming the data or using non-parametric testing if applicable. Hopefully this has been instructive or even maybe interesting for you. As I always say at the end of these things, thanks for your attention. maybe go fix yourself a cup of tea or a cup of coffee and relax. Hopefully let this information sink in. If you have questions, let me know in class or in the comments section. I'll do my best to respond to them. Thanks very much. Bye-bye.